Welcome back. OLG model, second lecture. This is a very, very important model. Doesn't get enough attention in many courses. I think it's worth speaking about for at least 3 lectures. And it's because it basically begins to show that economics is about conflicts. It's about heterogeneity and conflicts. It's very difficult to make everything understandable with a single representative agent. We like to do that because it's simple, and simple is better if you can have it. But in the case of the OLG model, we have a first set of conflicts. We have a distributional conflict, a functional distribution of income, capitalists versus workers. But the interesting thing about this model is that's coinciding with the age of the agents. So agents have 2 different ages in this world. You're young and then you're old, and if you're young, you're a worker, and if you're old, you're a capitalist because you used some of your savings to be a capitalist in the second period. That may make you think, well, is that very realistic? It turns out that in a lot of industrial countries, old people own means of production, and they use that to sustain themselves, either directly or indirectly, through their pension system. In a country like Sweden, or in Norway or Switzerland, where pensions are more funded than in other countries, we'll talk about that, it makes a lot of sense. Okay, and therefore this conflict between old and young, it shows up in a lot of other places, like the future of the earth, the way you care about your children, if you have any, or your children's children that are to come. These are all interesting questions that the OLG model can explain and talk about, not necessarily exhaustively, but at least give us an idea of where the discussion is coming from. So today I'm going to talk about the last lecture briefly, since we wasted some time. I'll remind you what the underlying assumptions are. Again, simplicity has a premium in economics. It allows us to cut through this incredible complexity we have in our life and just get to what are the common notions and incentives to do various things. And if people behave economically, not necessarily exclusively that way, but if they have some economic incentives that are operative, how will they behave? And the market form is important because we'll first talk about the decentralized solution. Old people and young people meet once. They make an exchange, and then this determines factor prices, and it determines the incentive to save in the future, and it determines the amount of money you can use, money in the sense of resources, because there's no money in this model, to consume in the future. So there's really simple, and economics is about training us to think clearly and make arguments clearly, and later we can make them complicated, and we can confuse people if we want. Remember what Joan Robinson said? Remember Joan Robinson? If you didn't get it, check the notes or check your neighbor's notes. We'll talk about the decentralized market equilibrium therefore first, and then I'll make an allusion to this idea of the golden rule, because Phelps had this idea. Maybe it's interesting to ask if the solo model gives us the right answer, because it's a positive model. It's not telling us what we should be doing. And then if you ask the normative question, what is the right way to do this? If we could command the generations to do this and that, to save this much and to invest this much, what would happen? Could we do better? Could we take more the welfare of future generations into account? Again, for the environmental question, this is absolutely crucial. This is a really great question. That's why this model keeps coming back like Groundhog Day. It keeps coming back again and again and again because it's just so interesting, right? Our children's children haven't been born yet, but we're making a mess of this world. It's the same idea of the OLG model. You do things today in a decentralized way, and you affect people's welfare in the future who aren't at the table to negotiate. So that's why this model is so important. Again, Paul Samuelson invented the model, although Allais, the French guy, claims to have thought of it, and I think he gets some credit for it. He did get a Nobel Prize at some point. And then what we're going to look at today is the Diamond implementation. Peter Diamond, another Nobel Prize laureate, implemented this model using capital as the vehicle for savings. Capital. Okay, so that's just a quick. So the golden rule is basically going to be questioned again, or we're going to ask the golden rule question by saying, well, in a decentralized economy, do agents acting individually actually reach the right path. And if the planner could choose the path, just directing people to do stuff, no choice involved, in a command economy, we call it, what would be the outcome in that case? And it turns out that under certain cases, the private equilibrium can attain a golden rule type of outcome. But the golden rule is kind of like the golden rule. It's better than most of what we end up doing. So we need to look at that carefully and what it implies. It also implies something for the real interest rate. We're already talking about interest rates now. Macro is all about interest rates. And the real interest rate is the one you really have to pay after you shave away the inflation, the veil of inflation, what's left over. And what determines that? Right? We already have an idea from last week. And that's going to be one of the fascinating questions that's dogging economists across the world. And I'll try to sell this social planner's optimum in a very non-ideological way. I mean, there are a lot of people who think this is the appeal to central planner. A lot of people who are anti-central planners say, you know, capitalism is proof that the planned economy doesn't work. Well, this is an economist trying to be as neutral as possible and ask the objective question, suppose we could do it, what would we do? And that would be the benchmark. Okay, that's the plan for today. And if I have time, I'll talk about policy. Okay, I'd like to go quickly, but of course the technology failed us again. But we'll see if we can catch up. Okay, so we talked about comparative statics and convergence, and in the section, I think you mentioned that a little bit more. Remember the rule of 70? You know, how long does it take to close half the gap? Or how long does it take to grow twice as large? It's a very interesting result that we should remember. The golden rule, we talked about this factor price frontier, which will be very, very important today as a first theory of neoclassical distribution of income. So again, we're not looking at who owns the capital, but whoever does own the capital will get a rate of return based on marginal productivity. That's the marginalist or neoclassical theory of functional income distribution. Wages receive the marginal product of labor, and in a constant returns to scale production function world, those exhaust the output. There's nothing left, right? That's really important for you to remember that. A lot of people don't kind of accept that. If you have market power, that's a different world. We can add that. It doesn't change anything about the production function, because to produce anything, you need to have a production technology, right? If you want to, regardless of what you're producing. So that's, you know, these minimalist assumptions can deliver a very powerful result, and then we can come back and shoot it down if we want when we get to be finished with this course, right? That's, remember, Joan Robinson, remember what she said. So this model is based on Microfoundations. We're going to talk about the motive to save, the motive to use capital in production, and those will come together in a market equilibrium. We'll have two curves in this model today that intersect, and they will give us basically a factor price combination which describes the equilibrium in a decentralized market, the path of wages and the path of the rate of return on capital. And over time, this is sort of like a self-replicating system, because the young people today will work, produce, earn, and save some, and that saving they will use to buy the capital from the old people who are leaving the stage, and when they become old, they'll be able to rent it to the capitalists of the next, to the producers of the next period that will use the capital with the labor of the young of the next generation. So this sort of logic gives rise to what we call a difference equation. Okay, when values of a certain variable depend on their past in a very mechanistic way, it's called a difference equation. This will be a nonlinear difference equation. So if you switch the system on, it kind of generates future values in a very in a deterministic way. And that'll be sort of defined by the logic of the model. Savings behavior by young people and the implied capital stock when those young people become old. Okay, so let's develop that model in detail. Remember, it's designed to understand capital formation, first principles, instead of using the solo, that's an undergraduate model. So your graduate students now, you're pushing the limits of your intelligence and interest in economics and trying to see if we can do better than this. But first, let's understand what we have to do. It's a way of understanding growth dynamics and the conflict between generations that can arise. You can extend this model in many ways. You can actually incorporate uncertainty. It's not an Achilles heel this model does not address uncertainty explicitly, but it does increase the complexity. It's already kind of complex enough. I mean, I've been doing this for like 30 years, and I have a calibration, what I think is appropriate for people of your age and interest on average. I'm not pitching to the marginal interest, I'm pitching to the average interest, because I don't want to drive you away, right? I want to attract you. I want you to get excited about this stuff. And if I'm successful in any way, I'll be a very happy person. So you can use this to think about bequests, so we can have the generations that are old actually leaving something for the future generations. Even though they don't have any children in this model, you can still imagine they decide just to make a gift to a church or a mosque or whatever, and use that as it makes them happy. It doesn't change the logic of the model either. Okay, but it changes savings behavior, because if you have a bequest motive, you're going to want to save more. You're not going to eat it all yourself. You're going to actually give some to your descendants or whatever. So there's a lot of ingenious implementations of this model. You have altruism, again, thinking about other people, but the core of the OLG model is I live 2 periods, I care about myself, and I care about myself in the next period. That's really important. And because I don't want to starve in the second period, I save in the first period. And how do I save? Samuelson, in his ingenious invention of this model, used money, paper, fiat money. And we'll come back to that topic later. Okay, that's because even if people agree to use the fiat money, it works. It works to exchange goods across generations. But we're going to pull back from that. We're going to use a productive asset as the modus of transferring resources to the future. We're going to use capital, the very capital that Solow talks about in his model. Okay, so that's where we're going today. And there are lots of policy questions you can answer. I already talked about the climate crisis, but we can talk about pensions. We can talk about the effects of labor taxation. We can even talk about bubbles, the housing bubble. Remember, a generation in this model is like 20 or 30 years. If you really want to implement this model, we're talking about 30 years first generation, 30 years second generation. You start working when you're maybe 20 or 30. So it kind of works, right? But again, we have to think elastically. Generations don't have to be exactly the same length. They just have to be overlapping, and they have to give rise to a double coincidence of wants. Somebody wants to save, and somebody wants to eat. Old people want to eat, and the young people want to save. That's as simple as you can get. The notation I went through already, just to remind you, little n, growth rate of the population, is an important driver in this model. There are always new people coming on board, okay, and there are always people leaving, and if the net effect of growth is n per period, we're going to have successive generations of larger size by a factor of 1 plus little n. Consumption in the first and second period, C1 and C2, at time t correspond to different agents. So C1t is the consumption of the young, and C2t is the consumption of the old at the same time. Both of those people have a claim on resources that are being produced today, because the stuff that's being produced today, per se, is either eaten or saved. And old people don't want to save. So you get the idea, okay? It's a decentralized market, so we have a wage, and the wage is what the young people who supply 1 unit of labor get paid in a competitive market. And R, big R, capital R, is the gross rate of return, because when you're old and you save 1 unit of capital, when you're old, you can trade in the 1 unit of capital back for consumption. Okay, so you know, it's not the little r, it's not the little interest rate, it's not the net interest rate. You're actually getting the whole thing to consume. So if I buy a Mercedes-Benz in the first period and I rent it out to some taxi driver when I'm old, I'll basically use that income in its entirety, because I won't leave any leftovers afterwards. Okay, so that's why we use 1 plus little r, the so-called gross interest rate, as the incentive for the old folks to save, or to young people looking into their older self to save. Capital depreciates at rate delta. Okay, this is like if you think about the Mercedes you buy when you're young as a vehicle for saving, or the apartment you buy, there's a depreciation rate applied to that. Okay, there's a private discount factor. That's the last line. That refers to your impatience. So if beta is very close to 1, then you value tomorrow's utility pretty much the same as today's. But if you're impatient, beta is going to be less than 1, possibly significantly less than 1. And one transform of beta would be to take beta inverse minus 1, and that would be the so-called discount rate, private subjective discount rate. Okay? So these are things you might have encountered when you were undergraduates. It's a measure of impatience. Okay? But again, we're trying to make this as simple as possible, but not too simple. Firms we already talked about. Firms hire capital and labor. These firms just exist out there. You know, this is like one of these veils. There will be activity. The owners of the capital and labor are the ones that earn the income. The firms are just kind of, it's just sort of a veil that organizes the production. This is not a factor of production. Again, a simplification that Samuelson and especially Diamond accepted. Diamond sort of organized in his paper in a very elegant way. Because of constant returns to scale, those payments will exhaust the product, and we talked about that as being the factor price frontier. So one of the curves that I'm going to draw today is the factor price frontier. It's this conflict between capital and labor. If capital gets paid more, labor gets paid less. If labor gets paid more, capital gets paid less, holding the technology constant, right? And that's an efficiency statement, but it's also a statement about factor remuneration at the marginal product. So you can derive that using neoclassical assumptions. You can also look empirically. It's like I said already, it was already kind of out there in the days of Ricardo. And he didn't even have a production function in his head. He was thinking about linear Leontief type production functions. So constant returns to scale gives rise to that factor price frontier. It's kind of ugly neoclassical theory. In the section, you'll probably go through it again. Why is that thing negatively sloped? Well, if firms pay marginal product to the labor and to capital, that's the way it is. If you want to give the labor more and be efficient, you're going to have to give capital less using the same technology. Now, if you improve the technology, the FPF can shift outward, right? We did that last week. I say ugly because it's not elegant, but everything else is complicated, more complicated than we need to be. So you could have a labor union, you can have an ugly monopsonistic capitalist in a one company town. You can have the government intervening this way and that way, but in the end, the production function stands behind everything. If we don't produce, we can't pay anyone. And a hard-nosed economist understands that, right? All welfare comes from wealth somehow. Even if we want to clean up the environment, we need to produce something to do that, and then we need to use capital and labor. So we can't get around that very hard, ugly fact. So it's always a conflict. It's going to be a conflict here between capital and labor, and the next part of my derivation is going to involve the conflict between young and old people, because young people are the ones who work, and the old people are the ones that just live off the savings they've accumulated in their previous youth. Everybody has to go through the washing machine. Okay, everyone has to work hard when they're young, and they get to enjoy the fruits of their labor when they're old. Again, no government yet. So we already have one theory of remuneration, or one relationship, and that's the diagram I want you to think of. And remember, the slope at any point along that convex curve to the origin is the capital-labor ratio. I can tell a logical story why that's the case, but it's also formally the case. The steeper at a point where the curve is very steep, the implicit capital-labor ratio is very high because wages are very high, the rate of return on capital is very low. And vice versa, when we're at the south east part of this curve, the wages are paid to workers are very low, the rate of return to capital is very high at a constant technology. So these are just combinations. And again, it's assuming a smooth trade-off. It's possible to use more capital-intensive or less capital-intensive methods of production. Okay? Any questions about that? This is one of the most beautiful things I learned when I was in graduate school, right? It took me a few times to repeat it. Sometimes you have to write these things out, use the calculus, and you get it, okay? Add depreciation. So this is a fact of life. If you add depreciation, the amount of output that's available for everyone is less because every year we lose some capital through wear and tear. So I can't pay that as labor income, I can't pay that as capital income, it just evaporates. So if you go to Cuba, I go to Cuba every year, I see what happens after 50 years of depreciation. Some of those buildings look pretty bad, okay? It is really the sun of Cuba and the neglect of taking care of those buildings, it just dissolves. Frau Merkel, the famous Bundeskanzler, once talked of von der Substanz leben. It does look like that. And this building, when I first came to Berlin in 1993, looked like that. And then you had lots of investment and you had to push it out. So think of the factor of price frontier. If you add depreciation, it means the rate of return on capital is lower for a given wage, or the wage is lower for a given rate of return. Okay, that should be fairly easy to swallow. Now, I've only talked about the payment of factors, but now we have to talk about the interaction. I alluded to it already in the last lecture. The savings of the young generation. They come into the world, they're working. Why do they want to save? Because they want to smooth their consumption over the 2 periods of life, and they take one decision when they're young. So it's a really, really simple model. It's the simplest you can understand. They maximize their utility over 2 periods, appropriately weighted with the beta. The beta is the weight. You know, beta is less than 1, could be equal to 1. We're going to make it less than 1 strictly. It's also positive. So we care about the future, but we care potentially less about the future than the present. We're impatient. And this is me deciding for myself. So you see it's CT 1T for today, and I'm planning my consumption for tomorrow of ni. Right? C2T plus 1. And I have to obey a budget constraint because I can only consume tomorrow what I saved today plus the rate of return that's going to be applied tomorrow. So there's always a budget constraint. Another hard-nosed, depressing fact about economics is we have budget constraints. You know, if we put out lots of money to some group of people, we're going to have to get it from somewhere else. There's no other way. Get it from the future, get it from the present. We'll talk about that next week. There's the budget constraint. What I'm going to be able to eat tomorrow is basically my savings today times the rate of return on capital tomorrow. The rate of return means the gross rate of return that after the taxi driver has taken my car and driven it through the city a whole 20 years, what do I get back? I get a car that's going to be worth a little bit less because of depreciation, but it's going to be productive, and I'm going to get the fruits of that productivity because I'm giving the taxi driver the ability to use it to get the taxi business running. So the marginal product of capital is positive, and that's giving rise to this gross rate of interest rate. If I subtract 1 off, it's going to be close to what we call an interest rate. If we adjust for appreciation, it will be exactly that. So that's where we're going. Someone had a question. Yeah? It's 1. Subtract 1 from big R and you get little r. Well, you know, in the real world, we don't, we talk about rates of return as I put in $1, what do I get back? I get $1, of course, but what's the extra? And that's the little r, the little rate of interest. Okay, I'm trying to stick with the notation as much as possible, but I have to remember, in an OLG model, you get the whole thing back. You know, if depreciation is 100%, if the guy doesn't crash your car, you get the car back. It's not worth as much as it was before, and you're not going to be able to get so much consumption when you trade it, but it's going to be something. Okay? Yeah? Why do we use what? The discount factor. Yeah, because you live 2 periods, and we're trying to be as neutral as possible as to how we value the consumption today and tomorrow. So we use the same function u, that's called a time-separable utility function, and beta is compressing all the impatience that we might have. So if I'm completely indifferent, then beta would be equal to 1. You would be indifferent between utility tomorrow and utility today. But if I'm impatient, then I'd I value utility tomorrow a little bit less than I value today's utility. It's what we call impatience, right? And it's going to be a very important property, okay? So if you have problems with it, please ask me again and again and again. These are, and there's a whole literature on this, on trying to think about impatience, whether it's rational impatience or irrational impatience, or it's impetuous impatience, okay? We want impatience that is consistent with our future self. That's why using a discount is an interesting way of attacking that problem. When you say, I'm going to save tomorrow, and then tomorrow comes, are you still going to save? Is your plan for tomorrow consistent with yourself in reality tomorrow? Or will you say, maybe not? Okay, so there's a lot of behavior in economics that we study, addiction, for example. You say, I'm going to give up smoking next week. And then next week comes, I'll put it off. So there are utility functions that can capture that, like hyperbolic discounting and whatever. But you have this contradiction. Your inner self that you face in one period is not the same self that you are when you took the decision. And we don't like that because it's inconsistent. So take that, put it in your filing cabinet, and maybe at the end of the semester you can come back to me and I'll tell you who to talk to if you want to study that. Okay, so it's behavioral economics, when people deviate from the benchmark of Homo economicus. It's got a lot of bad press lately, but I'm actually not responsible for that. I think there's a lot you can do with Homo economicus. Can't do everything, but you can certainly organize your thoughts. Okay? So that was a little lecture on. Okay? Now, you asked me about this, how we feel about our consumption. This is cooking it down to the properties of a constant function over time. So your utility function today is assumed to be the same as tomorrow. It doesn't have to be. But then I have to learn more about you and your future self, and I don't care about you and your future self. I just want to get this problem down. And I want to understand something very, very clear. So I can use a general utility function and I get the same answer, but it's not as crisp. Okay? This is called time-separable utility. So if you like macro, someday you'll have an infinite sum of time-separable utilities from each period from now till infinity, or you think about your generations. And we'll talk about something like that in a couple of lectures. So if I do the right thing, I'm going to try to optimize that. So look at it. It's a constrained optimization problem. What's your first reaction as a microeconomist? What would you do? Lagrange, le français fameux, sacre bleu. This guy has motivated economics literally for 150 years, right? Why? Because it's taking an optimization problem with hardcore restrictions. I can't choose any point I like. Obviously, if I want to make myself as happy as possible, I'd choose infinite consumption in both periods. But we face a budget constraint. And the budget constraint gives rise to the necessity of using a Lagrange approach, or you can subvert Lagrange, you can circumvent Lagrange by just substituting to eliminate the constraint from the problem. That's what I'm going to do here. Later on, we will use the Lagrange multiplier ad infinitum. But why bother torturing ourselves? You should understand that both can be done. If you're clever, sometimes you can actually avoid using two, but Lagrange multipliers have wonderful interpretations. Even though we can't see them, we can't put our hands on them, they represent certain valuations at the optimum that are incredibly important. So keep that in mind as well. Yes?
Sorry about the beta. Is it between 0 and 1?
Yes.
Okay.
Absolutely.
It's always like that.
Yeah, we're going to assume it, because otherwise people are acting kind of strange. So but it's not, just because it's strange doesn't mean it's wrong. we just want to restrict ourselves to average behavior. Those last two derivatives are important because they give us the concave shape. Okay, so I'm going to do the substitution in what we call unconstrained form. So I will define S as the savings of the young person, the person when young, living 2 periods. And this person is basically going to choose S. Now, see what I've done? I've eliminated C completely, but C is still there. C is still the argument of both of those two periods. Okay, but I've just substituted it so we can still, what matters to this person is consumption, but it's clear that saving more today means consuming less today. And saving more today means consuming more tomorrow. Saving more today means consuming more tomorrow. Did I say it right? It's a trade-off. And there's only one choice variable. So it's easy. It's easy. We can use calculus and derive first-order conditions quite simply. If you do the Lagrange approach, you'll have this Lagrange multiplier, and then you'll eliminate it using the first-order conditions, and you'll get the same answer. And we'll save that for later. And the first-order condition has this lovely intuition, which is, if I'm doing the right thing, the marginal utility of consumption today for the young person is going to be very, very related to the marginal cost of doing that in the second period. In fact, it should be right. If I'm doing the optimum, they should be equal. I should be indifferent between moving a little bit of consumption between my plan for consumption today and consumption tomorrow. That's the definition of optimality. Okay, so that first order condition characterizes that. That's a statement of the optimal behavior of the agent. Okay, so if that holds, that restriction is going to give me a relationship between S, my optimal choice, and all the other things that I'm taking as given, such as, what am I taking given as a young person saving today? The wage. And the rate of return on capital. And it's got a T plus 1 because it means that I'm looking at what's going to be paid tomorrow as a gross return for the savings today. And it assumes perfect foresight. We already apologized for that. You've got to start somewhere. Got to start somewhere. Because this is like that. A lot of people save a lot today and then end up choking when they realize, man, I really should have done something different. But that's a world of uncertainty where you can have regrets. You know, you can make mistakes in a world of uncertainty. But in a world of certainty, there's no regrets. Now, I told you these things stand for consumption, so I can substitute back for the ST, and I get exactly this condition. So you should really write this down if you haven't already. And I'm now putting the old slides online beforehand, so if you're really, really ehrgeizig, you can download them beforehand. Or you can look at them in real time right now. But it's not the same. I always change the slides for every year because I like to show you that I'm actually trying to work for my money here. Okay? So note what we've got. We've got the marginal utility of consumption today when I'm young is equal to the marginal utility of consumption when I'm old, but it's multiplied up by the fact that if I save today, I get more goods when I'm old, so they get valued at a higher rate, but then I'm impatient, so I reduce it by beta. Okay, so it's kind of a battle between beta and R. The return for savings and my impatience. That's an old-fashioned idea. It goes back to Irving Fisher, an American economist in the 1920s. Okay, so this is really basic stuff. At the optimum, the contribution of an extra unit of consumption to my utility today equals the equivalent of saving that extra unit, getting the rate of return, eating it tomorrow, and discounting it. Now remember, when I say tomorrow, I'm talking about 20, 30-year generations. But again, it doesn't matter. We do see people doing this. Savings in the world is enormous. Somebody has to own the capital. Somebody owns that building over there. Somebody owns all the apartments. Somebody owns this building. And that gets passed on from generation to generation. There may be some inequality in that distribution, but in this model, we're not going to talk about that. We're going to talk about the fundamental incentive for each of us to try to do something to better our outcome in the future. And if we don't do it, we're going to ask our government to do it for us. Right? That's why we have pension systems. So how do I figure out the way this curve looks? I've got a savings function here that's implicitly defined. The first equation defines an implicit function. Okay, it relates, like we said already, savings to the rate of return and to the wage. and to the shape of my utility function, of course, but this function is implicitly defined, and we use calculus to figure out what it looks like. We can differentiate that first order condition totally, and we can solve for ds dw and ds dr. Those are the responses of savings to a change in the wage and a change in the interest rate. It's called comparative statics. It's a local property because this function can be kind of unusual looking, but around the point of linearization, we say, we can describe using calculus the way it behaves. Why is that interesting? Hell, I would like to know if raising my wage would raise my savings, because if we pay more to the workers today, they'll have more to spend on consumption today and tomorrow. But what happens if the interest rate rises? Do I save more or less? Does anybody know? Did you watch the video? It's ambiguous. And why is it ambiguous? That's the hard part. Explaining it to a person at a cocktail party or at a club with the loud music. How do you explain to them why an interest rate increase in Germany would have an ambiguous effect? Please.
Sort of raises your lifetime income. So you could say, okay, now I'm richer, now the interest rate is higher, so I consume today more, and so save less, but then also I have a higher incentive to save. So they're like moving against these effects.
Exactly. We have two conflicting effects. One is an income effect, one you described first, and then there's a substitution effect, which says that, hey, future consumption is cheaper. If I save more today, I get more consumption tomorrow, right? And they can cancel out. In certain special cases, they do cancel out, exactly. Okay? And otherwise, we have to go to the data and estimate the behavior of individual households, and this is done all the time, how people react to a change in savings. Germany is a country that has lots of savings, and it's very, very controversial what an increase in savings does, interest rate does to savings. Okay. So we can write this implicit function as a function of the current wage and the current rate of rate of return on capital. And I'm just going to write that as S. That's going to be my implicit function. So in many cases you can solve for it. In life is not so friendly to us. Most of the time you have to use an implicit differentiation argument at the local point to see how this function behaves, because you can move from one regime where you have the income effect dominating to one where the substitution effect dominates, or vice versa. Okay, don't want to be too specific about this. Okay, so this is and it turns out that we'll probably expect the effect to be negative, or at least large enough algebraically not to cause the model to be unstable. I love living in Berlin. It's like you're really at the center of the world here. At least we're not having a demonstration today. Okay. So now let's find an equilibrium. We have two relationships. We have the factor price frontier, and then we have the incentive of people to save. If you save, then that's tomorrow's capital. That means tomorrow's rate of return will be determined by your savings today. So we have two relationships, and when you have two relationships in economics, you're usually in business. You can write down two curves, and you can let them intersect. If they do intersect, what's the property of the intersection? Is it stable? Because there's a temporal aspect. If I have a higher wage today, I save more for sure, and that means more capital tomorrow. What does that do to the rate of return tomorrow? It presses it down. That means that people in the future are going to get less rate of return incentive to save. We have to interact those two problems. So to describe the equilibrium, the young and the old people meet exactly once. Leopold will go into detail on this, especially when we start talking about money. You could talk about money in these terms as well. Money can be expressed as the outcome of overlapping generations of people trading money for goods, and you basically accept the money because you think it's going to be worth something when you want to buy the goods, right? It's wonderful, but now I'm just talking about capital. No money in this model. It's money free. Trading occurs. Perfect foresight is assumed. It's not decisive, believe me. The most important thing is we have intertemporal trade. Already talked about it. I'm reacting to the incentives to push resources into the future because I want to eat tomorrow, and as doing so, I actually affect the productivity of the economy in the future because I'm giving it more capital or maybe less capital. So impatient economies will tend to have less capital around on average, because people are not willing to make the sacrifice. They want to consume now. We can actually show that in this model. And I said we can use this model to do all sorts of things. You can think about the environment as being a good that we transmit to future generations, right? You can write the whole model in terms of some consumed good and the environment. The environment is passed on exactly like the capital stock. And you can think, well, are we going to have a good outcome if people don't care about their future generation, their offspring, or if they're just impatient? Well, that's exactly what this model can help us think about. But right now we'll talk about capital, really sort of hard-nosed economics. So under certain conditions, I get a cancellation of the income and substitution effects, and that's the famous Cobb-Douglas function, or log utility function. It's better to call it log utility if you don't get the reference, but think of ln of c as being the periodic utility function, and therefore the lifetime utility function would be ln of c plus beta times ln of c in the second period. Under those conditions, and you can do it in your sleep, basically, it's very easy. You get a constant savings rate. Regardless of what your wage is, you're going to save beta divided by 1 plus beta of that wage. Okay, that's just one example. A lot of people use that to teach with. I just like to use it as an example, but it's a special example. Most examples will not, or most real-world examples would not be characterized very well by that. So now we can move to a goods market equilibrium and talk about what happens. Today's capital stock gives rise to a factor price trade-off. It gives rise to productivity, a wage today. The young of today will save. That will give rise to the capital stock tomorrow. And we can characterize that as goods market equilibrium. So this is the first example of a difference equation. So the capital stock tomorrow, KT plus 1, is equal to the population today of young people who are saving, and that's ST, and that's a function, capital S, of omega and R. So look carefully at that. You see something that's quite interesting. You see that the omega today and R tomorrow are kind of determining K tomorrow. So there's this intergenerational link that's given rise to by the transmission to the market price of labor and capital. So if I divide by NT plus 1 to get a per capita left-hand side, I get a right-hand side that is incredibly elegant. It's basically a constant divided into the savings function given the factor and price incentives that the young people face in period T. Remember, the young people today, when they're deciding how much to save, are working for a wage, and they know that their savings will give rise to an interest rate tomorrow. Okay? So this is like a machine. You kick this thing and let it run for a while, and you get some sort of dynamics. And we're going to look at that, because there will be a resting point when the KT plus 1 is equal to KT is equal to KT minus 1, and WT is equal to WT minus 1 is equal to WT plus 1, and then we have reached what's called a steady state. That's going to be the intersection of two curves. Okay, and if you can accept that, then we can actually do lots of other things. We can do comparative statics experiments. We can incentivize people to save more or less. We can tax them. We can transfer money from young to old. What's that called? It's called redistribution, but what in the real world, what's it called? Sozialversicherung. It's called the pension system. I mean, I don't know if you know this, but if you work for money, the government doesn't take your money and put it in a machine. It actually gives it to old people. That's called pay as you go. And that's exactly what could circumvent the incentives of people when young to save, because they know the government's going to take care of them when they're old. So that's one of the key questions we can start looking at, is the effect of pension systems that are unfunded or imperfectly funded. I'm not saying it's bad, because in a sense the government's trying to trying to ride the wave of population. As long as the population is growing in those worlds, it's fine. It can work. But when people stop having babies, when demographics start to peter out, then we have an issue. Okay, then you get the conflict between the generations. Now, there are two questions. Yes?
I think he meant the sentence, the capital structure amongst equals, the same expectation.
Yeah. So the young people have to save, right? And they have to acquire the capital from the old people, because the capital doesn't just come out of nowhere. The capital is a state variable. Okay, so it's out there, and if you defer some of your current production, you will get some capital, but you also have the capital that you can acquire from the old people. So your wage enables you to buy the capital from the old people. And the old people sell you that capital, and you can also increase that capital. So there's a way to, it's called investment. You learned about it in the solo model. So that's part of this. I've tried to, it's suppressed implicitly because there's only GDP out there, and you can either consume it or you can invest it. So if you're not consuming it, obviously you're going to be investing it. That's the flow, and then you've got the building that you've inherited from the past. So this is a much more general framework. You can make depreciation very high, and you can have a very sort of, everyone's saving in the form of computers, and then the computers are obsolete every period, but it doesn't change the logic at all. So let me try to draw this picture. Maybe this will help you a little bit, okay? We already have the gross return of capital because it comes from our factor price frontier, right? So we already, if you have depreciation, you can add depreciation. It doesn't change anything. It gives us the second link between the interest rate and the wage that are paid today. And then we can use calculus to look at the slope of this relationship, okay? Because it doesn't have to, we don't even know it's negative. And that's why we need a reaction of the young people to save more if interest rates rise. Okay, so if the income effect dominates in a big way, we have a problem with stability of this model. But again, like I say, in the end, the data are pretty supportive. If we use calculus, we can show that the slope of this goods market equilibrium relationship is also negative. And how do I know that? Well, I know the second derivative of the production function is negative. S sub W is positive, so the denominator is negative, and the numerator is also going to be positive. So as long as people have well-behaved savings functions, we're going to have a negatively sloped goods market equilibrium line. Goods market equilibrium means when you're young, you save, and the savings is essentially acquired from the old people who are simultaneously alive today. Okay, so we have two negatively sloped curves, and we're going to look at that. This is technical. I think we already discussed it. It's important to know you want to have savings responding positively to the interest rate that's paid tomorrow. And again, we discussed this already. So both of these can be expressed in the form of curves, and that's what I'm going to do right now. This is the goods market equilibrium curve. The other one we already drew. That was the FPF. So those two will presumably intersect somewhere. Okay, and that gives us a nice idea of where we're going. But just to make sure we're on the same page, this curve is basically a relationship between the wage paid today and the expected rate of return on capital and that rate of return on capital. And if the wage is high today, there'll be more savings today. The marginal product of capital is declining in the capital stock, so the rate of return on capital tomorrow will be lower. Right? That's the logic. So in steady state, these are equal. So we're going to look for an intersection of those two curves and hope that this intersection is stable. Remember, in the solo model, we had all these things in the background, but we never tried to explain them. We didn't explain where savings was coming from. We just kind of came out of the blue. You can augment this model. You can add technical progress in the same way we did before. The wage will grow at the rate of technical progress. GDP per capita will grow at the rate of technical progress. The capital stock will grow at the rate of technical progress. So this model is completely conformable with the solo model. A lot of people would call this the first apology for the Solow model, the first account of the Solow model, trying to make it work. So that's it. That's the diagram you want to be thinking about. Okay? The diagram gives rise to a steady state wage. And here it's per capita. So I'll shut down technical progress right now. We'll just talk about the simple model. And we've got a rate of return. That intersection is a state where basically everything comes to rest. And unless there's a change in one of these underlying parameters, it's going to stay like that. We call that a steady state. Okay, so this is a good theory. It's a starting point for the realized distribution of income between young people and old people, or between capital and labor. And again, not looking at the possibility that distribution could matter in a different way. There might be a capitalist class and a working class, or there might be a middle class, and they may cross through age. But then you have to have a theory of how intergenerational inequality is transmitted. So people have done this. So you want to have you can have a multi-family model with dynastic generations of people saving for their kids, and some people get lucky and become very wealthy, and some people are very unlucky and don't make it. And you can discuss that. Again, we're more interested in determining the functional distribution of income. And if you want to go beyond that, then take a good course in growth theory, or go to a PhD program that actually specializes in these types of issues. Like Thomas Piketty, right? Done some very important work on this. But this is kind of one of the main vehicles we could use to look at this question. Because I could write down, in fact, Leopold and I have a problem set for you where we have two different classes. You can use the class lens to look at things and use this model to look at those things as well. Okay, so what happens if you're outside the equilibrium? What if you're outside the equilibrium? That's the question that always fascinates economists. What happens if I'm, let's see if I can do this. Suppose I'm here. What happens next? Again, this requires us to put our thinking caps on and understand what these graphs, these curves mean. So the blue curve stands for the trade-off between wage and rate of return at time t. Okay? So we can say with absolute certainty we're going to be there. The question is, what does this mean for savings behavior? Well, what do you think? What? Well, it's not going to be a goods market equilibrium, right? There's going to be incentive to, the wages are too low, there'll be too little capital, the rate of return on capital will rise, giving rise to more, giving rise to less capital, and that would lead to a lower interest rate. And that would give rise to higher wage in the next period, which would give rise to more savings and lower interest rate in the next period, which would give rise to more savings in the next period, and we would move in this way to this intersection point. And that's going to require that the second curve, the goods market equilibrium curve, is steeper than the factor price frontier. Otherwise, you will not have an equilibrium. Okay, so in time t, the FPF determines the factor price constellation. And then you ask, what's the consequence of this wage? Given that it's higher than the goods market equilibrium, so you'll have more savings, and that would press down the interest rate. Okay, and then given that, what's the implication for savings and the rest? And we can show this formally by just writing down a first-order difference equation expressing kt plus 1 as a function of kt. And kt is embedded in this savings function, in the following way. It's embedded in these two factor returns. It's embedded in this factor return, as you can see. If I plug in the value of omega t, it's equal to the GDP minus the capital stock per capita times the marginal product of capital, which is the rate of return on capital, and that would give rise to this dependence of KT plus 1 on KT. Okay? And similarly, this is implicitly defining this relationship between KT plus 1 and KT. The only way you can actually extract the relationship is to use calculus, because obviously KT plus 1 today is affecting today's KT plus 1 is affecting today's savings, which will affect tomorrow's KT plus 1, so they have to be consistent with each other. Okay, and that's the expression that we have here in front of us. Okay, so we can again take another condition where the wage is very high. Okay, so at R1, so I'm actually doing what I tried to do with my pointer before on the slide. So at R1, the savings that is forthcoming at R1 and omega 1 is insufficient to pay the wage that is being paid at W1. So the marginal product of labor falls to W2, and that wage leads to less savings through the income effect, and then there'll be less capital per capita, and therefore there'll be lower wage. Remember, the less capital intensive we have, the lower the wages, the lower the marginal product of labor is. Okay, so in that sense, converging from the left, we have the same type of step reaction that we had before. Okay, that was exactly what I said before. So you can read it off the slide. A low wage means too little capital invested, and therefore the wage will be lower. The rate of return on capital will be higher. There'll be more savings. More savings will raise the marginal product of capital, raise the wage, and the economy will converge from below. Okay, so it's just a statement that, and you can see intuitively, if the factor price frontier is not flatter than the goods market equilibrium curve, we won't have a stable equilibrium. Won't have this convergence. So that's kind of it's a fairly innocuous assumption. It's met by most of the models that we'll be looking at, but it's important to remember we're going to assume stability, otherwise the economy sort of veers out of control. So people, again, not taking into account what their savings does to the rate of return tomorrow for future generations can lead to unstable behavior, but for the most part, the economy will converge. Okay, so let's look at this stability condition can be written down using calculus. So if W star and R star are the steady state values, then around that steady state we need an increase in KT plus 1 to lead to a KT, in KT to lead to a response of KT plus 1 that's less than 1. That's another way of stating the stability condition. So if I could just somehow drop a little bit of extra KT on the economy, it wouldn't cause the economy to explode or to veer out of control. It would cause basically, through the savings behavior of individuals, the additional KT would lead to higher wages, would lead to more savings, but not so much savings that the economy would induce more capital in the second period. So you can see this income effect can't be too strong in this economy. And it's exactly this steepness versus flatness criterion. Okay, so I will just show you how an economist would look at this formally. You can take this, again, it's a nonlinear first order difference equation, expresses KT, which is is a variable of interest, as a function of KT in the past, or equivalently KT plus 1 as a function of KT. Okay, but it's a nonlinear function, and to find out that the slope of that relationship, we have to differentiate totally and solve for dk dt, and you get this. Okay, so we want that thing to be as we said before, less than 1. That's going to be kind of a formal condition. We won't do this on a final exam, but it's something to know. If you have the diagram and you want to see where the economy is going to stay and not veer off into another orphan or enter it to 0, then you need to impose that. Okay. So in the Cobb-Douglas case I gave you before, stability is okay, right? Cobb-Douglas production function, log utility, the stability condition is fulfilled. So I wanted to give you an introduction to log linearization as a tool. If you pursue macro in the long run, you're going to have to deal with this. We have lots of relationships like this one that are not necessarily linear. So can we make statements about the behavior of that model? And one way to do it is to take logs of both sides and then take a Taylor approximation, and you get something, you know. The first thing, if you take logs, you get a log of the capital stock on the left-hand side, and you get the log of the ratio. So you can see it's going to be all about the behavior of this S function, the savings function around the steady state or locally. So if you take a first-order Taylor approximation of this, you get the same answer, okay? But now we're looking at deviations of KT from the steady state value K star. Okay, so first-order Taylor approximation, I'm sure you've seen in your math review class, but it's basically taking advantage of the fact that any function that has a first derivative that's continuous, you can expand this function as approximated as a linear function of a small change or difference of that function from its steady state value as a function of the deviation of the variable of interest from its steady state. So here you're looking at KT plus 1 deviating from K star as a function of KT deviating from K star. You can see those are both like percentages. Okay, so that's why the logarithmic transformation is so useful. This object is exactly what we had before, and it's basically expressing the same stability condition. Okay, so I'm just repeating these conditions. We want the first derivative of the savings function with respect to omega to be positive, or W, and we need SR to be algebraically big enough. We'd like it to be positive, but it can also be negative. It just can't be too negative in absolute value. And then we have the stability condition. Let me give you some policy examples, right? So this is all about trying to use economics to help us make causal statements. If I change this, what happens to this? And then if you like the model, if you think the model is robust enough to withstand the test of time, like this one, then you can use it to answer a lot of questions. So we talked about impatience before, right? We talked about beta. Beta is this measure of impatience. The larger beta is the more patient you are, the higher beta is, the lower the discount rate, the subjective discount rate. Think of those two as inverse functions of each other. But you can think of other examples, comparative statics examples, using the OLG model. You can talk about a change in the depreciation rate. You can talk about a change in the population growth rate. You'll see later in the discussion we talk about the pension system. The pension system can be either a funded pension system or a pay-as-you-go system. A pay-as-you-go system kind of uses the new young people to fund the old people today. It's like you have this asset of people that are growing. And as long as the people are growing, it works. But if people stop growing or disappear, then you have a problem. Again, we can answer those questions using this model. You can also look at what happens if the rate of change in technical progress changes, which is a lot of what motivates the discussion today about negative interest rates, is that maybe technology isn't growing as fast in terms of its effectiveness as before, and that's affecting the interest rate. So let's just take an example of how you can use this model constructively. Okay, so consider this kind of tricky one, right? What happens if the depreciation rate of our capital that we're using to trade between generations suddenly increases? in an unexpected way. We can compare two economies with different rates of depreciation. Well, first off, both curves will be affected. Both curves will be affected. The factor price frontier will be shifted inward because you can't afford to pay the wages given the rate of return on capital. You can't afford the rate of return on capital given the wages because there's less to pass out. There's less to pay in terms of factor rewards. So the blue line shifts inward. And the second one is that the goods market equilibrium will shift inwards as well. Okay? It will shift inwards because of the negative effect the user cost of capital will have on savings, because it's less worth saving, so you're going to save less. Right? So both curves shift towards the inward, and you can see what happens. Both the rate of return on capital and the wage fall. Where it falls depends on the shift's extent. So you have to know more about the savings behavior to understand the extent to which the goods market equilibrium curve shifts to the left. But you can see that if it doesn't shift as much, then the wage will fall. Okay, there'll be less capital. Therefore, the capital intensity of the economy will fall, and the rate of interest will fall by less than it would in the other instance. So now here's the question that I'm going to leave you with today, but I have to throw it out there. Is this outcome the best we can do? Now remember, I'm saving when I'm young, I'm thinking about myself when I'm old. The capital I save will affect the productivity of laborers in the future, and I don't care about them. I mean, unfortunately, economics is about that. The first instance, people care about themselves, their families, and then we can deduce what that effects have on other people's behavior. It's mediated through the market, but it's a fact. If I save a lot today, there'll be a lot of capital tomorrow, and that'll affect wages tomorrow. They'll be higher, and I'll have more to consume myself, but I'm not going to think about those people who are benefiting from my savings. So we can ask the question, and a lot of people think this is an incredibly provocative question, could a social planner do better than that? And we're all free enough to write down our own mathematical problem and try to solve it. If we could we do better than the market outcome? Could we do better than this intersection of the two curves? And of course, the most important thing is, how do we treat those future generations? Is it fair? Because we have our own personal discounting of the future utility, but what if we're not really thinking about those future generations that are unborn? And they're out there, they're going to come on board some point. So is it a fair thing? Is there a social discount rate that we could think of? Okay, so we need to have some objective function that includes the generations yet unborn and their utility, and weight them in some way. So the problem becomes a bit more complex, and yet we can't cheat the budget constraint. The resource constraint of the economy will always bind, in a sense. We cannot cheat. I mean, there's only a certain amount of GDP. I can give it to you, I can give it to me, and you're old and I'm young, or vice versa. But there's always this trade-off. I can't cheat the budget constraint or the resource constraint. So the social planner can't do it either. It's not almighty. He can't sort of just choose whatever he wants, or she. Okay, so we'll take a very simple formulation of that. We're going to call this the social planner's problem. And the social planner will think of intertemporal optimality, but also intratemporal optimality. Am I treating the generations fairly? Okay, and again, this comes very close to this notion of environmental justice and all the rest. So I'm going to motivate this a little bit right now. Can we do that? Are we allowed to compare people's utility? Can I even, it's a presumption to do this, but if I maximize our utility together, I put a weight on your utility and a weight on mine. Should it be equal? Should I treat some people differently? We'll talk next week about Ramsey, a famous economist who actually said, no, you shouldn't. You shouldn't use a discount rate at all. It's immoral, especially people that haven't been born yet. But why should I get more weight than future generations? This is a philosophical question. And the currently old generation, how do you treat them? These people have already done their work and they're just sitting there living off our generosity, possibly, or their own clever savings policy. Okay, so we'll set up the central planner's problem as a benchmark just to judge whether the market outcome is anywhere close to doing what we think it does. Usually we think that markets do a good job of allocating resources. Well, here's a question that we have to answer. So here's the notation again, same notation as before, except now I'm going to add a social discount factor because maybe the social planner, she has a different weighting of utility across generations. Remember, she's looking at the lifetimes of many, many future generations and aggregating them to today and asking, can I change the policies of savings and investing capital to make people better off? We already know that's possible. You can invest too much. What do we call that? Dynamic inefficiency, right? That's a free lunch. If we save so much capital that we just scale back a little bit, we can eat that capital, we can drive the cars instead of renting them, we can use the computers for games instead of using them for work, shift the use of resources to consumption, and nobody loses. The other case is more painful. Dynamic efficiency means if you want more capital and get closer to some social optimum, someone's going to have to suffer. They're going to have to abstain from consumption for some periods. You have to tighten in the belt. Savings means not eating, putting the resources into building houses instead of making consumption. Okay? Now, there are no prices in this model, so this is really literally a planner's problem. This is like if you're a dyed-in-the-wool communist, this is what they dream about, right? All the technology's there. I just push the buttons and pull the strings, and it works, right? So we're giving them a chance to do this. And again, we're free to do this because we're economists. We can do that. We can make this assumption that we have the ability to control consumption today and consumption tomorrow for every generation under the resource constraint that no period allows people to consume beyond their means when added to across the age cohorts. So the old and the young in period T cannot consume more than is produced. Otherwise, you're breaking the rules. You can't break the rules. The social planner, she will choose a sequence. Remember, our little family chose savings today, implicitly consumption tomorrow and consumption today. Well, the social planner can choose sequence of consumptions for all generations when young and old. So that's the beauty of being the social planner. You can do whatever you want, okay? But you still have to obey the resource constraint. You can't break the bank. You gotta obey the rules, okay? So this one is simply a weighted average, and again, I'm putting a finite T, so I'm going to be generous to this social planner. There is an end of the world, capital T. So we're summing up these T generations from 0 to cap T minus 1, and each generation has utility of U of CT1T and beta plus U C2T plus 1. So each generation's utility, and then I'm adding them up. Okay, and I'm being fair. I'm letting each individual weight her utility or his utility intra-family wise, but then I'm weighting each family in a certain generation in this very general way. So if I really wanted to be nasty, I could put all the weight on the current generation, or I could put all the weight in the future generation. I will be much more specific later. I'll use a social planner's discount rate. Okay, so this C will be just simply CT will be simply 1 over 1 plus theta raised to the Tth power. It'll be just a social discount. But that'll make it very clear that the social planner, she has to also have a certain impatience, or maybe not. You know, that's what Ramsey worried about. Maybe we can't mistreat those future generations. And this is what you cannot cheat. Every period, the current output And the current capital stock, to answer your question, the capital stock is still there. It's just changing hands, okay? And we're just trading it for your effort. When you're young, you work for it, and you get to have a car, and then you give it to the next guy who wants to buy it for you so you can eat in the next period. It's really just a beautiful model. You cannot cheat that resource constraint. You're stuck with that. And it's every period. It's a sequence. In every T, this linkage between periods has to hold. You can't just invent another Humboldt University. You have to build it up. This building was built in 1905. I keep telling you that, but it's important to remember. It is a great example of intergenerational transfer of resources, because we're still using the building that the German Kaiser generation of 1905, Wilhelmine Germany, actually sweated to put together, right? And we're still using it. We're very grateful. Thank you, founders of the Humboldt University. Actually, it was the Handelshochschule. It wasn't even the Humboldt University. Back then, the Humboldt University didn't even exist. It was the Berliner Universität. Actually, before that, it was the Friedrich Wilhelm Universität zu Berlin. Okay, so it's like changing signs and rolling up different flags. This used to be the Handelshochschule. It was founded by business people, businessmen, old white men, basically. Right? 1905, they put their money together and started this place, and it failed in 1930. And it was taken over by the Berliner Universität. And then after the communist regime, it became the Sektion Sozial Wirtschaftswissenschaften, and now we have it, right? So the capital's still there. I mean, it looks a little bit nicer because we painted it, but it's basically the same building. So that's the kind of transfer that the second constraint is going to appeal to. And it's a fact. You can be a communist, you can be a liberal capitalist, Manchester City, whatever. You still have to obey this equation. You cannot evade that. I just want to provoke you, okay? Did I do that? So last slide, then we break, okay? Sorry it took so long. I'm going to make this assumption that the social planner has a discount rate, a social planner's discount rate, theta. Theta could be equal to beta inverse minus 1. It doesn't have to be. The social planner could be more or less patient than the individual family. All the families are the same, of course. And you have all sorts of interesting variations. So if there's a positive theta, that means the social planner actually cares less about the future generations. Right? So that's already an ethical question. Ramsey talked about that, and I'll talk about Ramsey next week. Okay? You could also care differently about persons because the number of persons is growing at rate n. So do you care about persons or generations? Think about it. Another philosophical question. But no matter what, the current capital stock is determined by the decisions that are taken in period T. Even if the social planner takes it, the social planner will determine how much consumption today for the young and the old and how much capital goes into the next period. And next week we'll describe that in detail, thinking about intergenerational altruism and selfishness. Okay? Any questions? My apologies. Look at the slides, watch the video. You have a question?
You said that this model can be kind of replicated for class differentiation.
Yeah, you can. It requires a bit of effort. It's a bit more complicated. And most importantly, you have to decide, how do people flip between classes? Or is a class just like you're either a rich person or a poor person forever? That's unrealistic. We know that you can switch, but then you have to use some transition process, like it could be random, could be luck, it could be skill. So it's directions you take are quite different. Okay, see you.